today, it is actually our tutorial and practical time, but since but for today, I will continue our lecture from chapter 1 last time, and then we will cover until 1 3 of your chapter 2, and then after that, and then we will do your tutorial. I think we do your tutorial first lah. After that, we proceed to the lecture. Okay, so the next Friday we will do your practical, but your first practical is actually also a lecture, but it is about the assembly language. Okay, so the assembly language will be used in your assignment letter. So so the next Friday there will be a lecture. There's still no practical because you need to know the theory first, and then baru you can do the practical. Okay, so can we proceed with the tutorial one? I will assign student lah to answer. Okay. Tutorial 1.
I thought lecture.
Huh? What? You haven't done the tutorial?
I thought today's. I thought.
Oh, you thought today is the lecture. Farah, have you done it? And Noel?
No.
Finished.
Oh. So you Noel?
Oh yeah.
Oh, not yet. Okay.
No, finish.
Mine not yet.
No. Farah, what? Pardon?
Mine not yet.
Oh, so all of you belum lah. Okay, so okay, so if like that, we proceed to our first lecture that we have left previously, which is okay, lecture 1. Okay, I will record our session first. Okay, so this Friday we will go through your tutorial lah. Huh?
Okay.
Please do your tutorial 1. But since today we will cover until until the logical I will share. The last part of the chapter 1. So this Friday I want you guys to finish the tutorial. The tutorial 1 lah, because last time I asked you guys to answer 1 until 8 kan. So now this Friday we will discuss all of the tutorial 1 lah. Okay, can you guys see my screen?
Yeah.
Okay. So we proceed to the lecture 1. Last time we were here. Okay, so previously we have covered the basic of the number system, and then we also learn how to convert all of the type of the number, and then we also learn how to do the arithmetic operations such as the addition, subtraction, and multiplications of the number system. And then now we will continue to this topic, which is the bitwise logical operations. Okay, so these bitwise logical operations, in this topic we will introduce about the logical operations. Okay, so in this we will learn about the diagram for logical operations. For example, the bitwise logical operation N. So there are two types of bitwise logical operation, which is and or. Sorry, three, not yeah. So there are three, and or and not. So the first bitwise logical operation is and. So it is represented by two sign, which is dot or this what macam the V terbalik ni. I don't know the name. Okay, so the N operation is represented by two sign, which is dot. For example, this one. For example, if the statement says that A and B, so you can use A dot B. Or you can also use the second sign, which is this V terbalik. So if the statement says A and B, then you can write as A V B. Okay. So this is the digital diagram. If you saw something like this, there's A and B, meaning this A and B. Okay, so the truth table that will represent this is if the tips are when they are F, either one, the answer will be F. Except except when both are T, barulah dia punya answer is T. Okay, for example, if you see here, if A is F and then B also F, so the answer of course F lah. But if A is F and then B is T, and then the answer also F because there's a F either in A or in B. Okay, so in the next example is A is T and then B is F. So the answer also F because there's a F what in both table in one of the table. Okay, so only when both are true and then the answer is the true. Okay, for so far, okay.
Yeah.
Okay.
I think learned before all these truth tables.
Oh yeah. So I think yeah also. But I don't remember which course. Do you remember which course? I think this is also in mathematics, right? You learn this in mathematics also. Yeah. So this is kind of easy lah. Okay, so we proceed to logical operation or. So it can be represented by the sign plus and then V, the normal V. Okay, so like A or B, you can write it as A plus B or A V, normal V and B. Okay, so this one lah. And then the sign, the diagram is the digital get diagram for this or operation is it is like this is like kite or a wow. If you know the macam layang-layang tu kan, so this is the diagram for or. So it is different with N because N is more similar to macam D, capital D, but this one is like error or kite. Okay, so this is the diagram lah. Okay, so for OR, as long as they are T, either either one of the components, so the answer will be true. Okay, so it is different from the N previously. So only when both are false, then the answer will be false. But as long as there's a T either in both component or either in one component, so it will be always true lah. Okay, so for example, F true, it should be true. True and false, it should be true. And then true and true, of course, it will be true lah. Okay, so after that, we proceed to the NOT, logical operations of NOT. So it is, there's only one, there's two sign that will representing the NOT, which is the apostrophe. This one is the apostrophe, and then this one. I also don't know the name of this. Okay, so you guys remember lah, this one cannot. Okay, so this for example, if not A, of course the other one lah. If the other one is C, then not A will be C. Okay, so this is the diagram, the digital get diagram for not. Okay, so for example, if not A, meaning if the component is only F and true, so if not A, meaning okay, sorry. If the A is F, then N not A is true. And then if the A is true and then the not A, of course, F lah. Okay, so I think you guys understand about that. Okay, so we proceed to the operator precedence. Okay, so meanings that which you need to prioritize first when you found this kind of expressions. I think we have learned this. This is the common rule in mathematics. So if you found something like this, the expressions is like this. So you need to find what is the not A, then barulah yang OR. Okay, so after that, for this kind of operation, then you need to solve inside the bracket first, which is the OR. After that, baru you find the not. This is the not. Okay, so for something like this, you have to find inside the bracket first. So this is the rule in mathematics, meaning you have to find the answer for N first. After that, baru you can consider the OR. The plus signs here, OR kan? So for this one, okay?
Okay.
Okay.
Okay. Okay, so we finish the chapter 1. So later, Friday, I want you guys to finish the tutorial 1 lah. Okay, so yes.
All the tutorial kan? The question 1 until question 8?
Yeah.
Oh, okay.
Because we already cover until bukan sampai habis sudah chapter 1, so yeah. Okay, so we proceed to lecture 2. This is actually because this lecture should be very long lah, 93 slide, and then it is very, I think it is technical lah. Maybe it will take time for us to for you to understand, because me also it takes time for me to understand, but I will try to explain as best as I can. And then this lecture we will divide it by 2. Meaning now we will cover but I think 1/3 lah. maybe until we finish this one. This is the topic that we will cover in this chapter, which is the data representations. Okay, so in this, the topic that will be covered is this one, the unsigned binary and binary code, and the binary code decimal representation, and then we will learn about the signed integer representations. So in this signed integer representation, we will learn three type of the way of you can calculate the signed integer. So we will learn about the signed integer later, and then after that we will learn until the overflow and carry condition lah. So next week. So next week we will cover this floating number, and hopefully we can finish this until the image data representation. Okay, so this is the topic lah. Okay, so I will cover this in this lecture first. Okay, so we proceed. Okay, so first, before we go deep into all of the calculations, I want to just introduce, I want to brief about what is the unsigned and signed binary. Signed and unsigned binary. Okay, so first, for this one, the lecture in our Google Classroom, I haven't updated yet because in this lecture, what I have now in my version, I already have some notes. So I will upload this later in our Google Classroom. I will update the lecture in our Google Classroom. So there are some notes that telling about the signed and unsigned integer or variable. Okay, so who among you have already learned or heard about signed and unsigned binary integer? Siapa yang pernah dengar? Have you learned it before?
A bit.
A bit? Oh, in what course?
In YouTube.
Apa? Di mana?
YouTube.
YouTube?
Yeah.
Oh, you learned it by yourself?
Yeah, just a bit.
Oh, Kelvin and Farah?
Oh, no.
I think have, but in Malay.
Oh, okay. Okay, so we will. I will tell briefly lah about this. Okay, so actually, what is the signed and unsigned binary integer? Okay, so they are when a variable such as integer can be represented in two ways, which is signed and unsigned. You guys can see my screen, my notes here. Okay. So the signed number use sign flag or can be distinguished between negative value and positive value, meaning the integer, any number that you need to put either negative or positive value is you call them as signed number. For example, temperature, because there's a positive and negative temperature. pH number, I mean the acidic or the alkaline punya number too, because there's a positive and negative kan. Okay, so that kind of number we called as signed number. While for the unsigned number meaning all positive. There are no negative number. Like our number, yeah, like our, I mean, the number that we use daily lah. Although there's a negative, but usually we will use some positive saja kan, unless we are calculating or unless we are calculating either temperature or the pH. Okay, so You can see if you want to know more, you can refer to this tutorial because I also learned it from there. Here. Okay, so here I want you guys to see this. So binary number or any integer, there are two ways of expressing it. Meaning there are unsigned representation. We can present the binary number into unsigned representations and signed representations. The difference between these two representations is unsigned presentations, it is on because the value is only positive, so they are unambiguous. Unambiguous meaning there are no overlap meaning or value. But for the signed representation, there are it is a little bit difference from the sign because it has two value, and then computer will hard to interpret the negative value. So that's why we are learning about the sign representation and sign representations, because the data representation, I mean, in this chapter, we are learning how computer will interpret or represent all of these numbers into binary, because computer only know about two numbers, kan, 1 and 0. So how the computer will convert all the negative value to 0 and 1, there will be three ways, which is the first way is sign magnitude form. So we will learn this later. But using this method, it also still can produce ambiguous result, because using these methods, there are two bit number of O's, meaning they are negative, because this method will produce negative and positive 0. Okay, so we will learn this. I will delve in the detail later. Okay, so and then the second method, the computer will convert the the sign type of integer is using the one complement form. Okay, so this method also produce ambiguous result, because it also produce two version of O, which is negative and positive O. And then after that, the expert come out with the two complement form, and then this method, it is successfully produce unambiguous result, which is there are only one version of 0. Okay, so we proceed. Okay, so enough with the introducing what is signed and unsigned binary. So remember, sign only has positive, unsigned only have positive value, but sign it will has two representation lah, which is the positive and negative. Okay, so for the unsigned binary integer type, so there are two approach how you will convert this type of number into binary, because we want computer to understand all of that positive that unsigned binary number, kan? Yeah. So we need to convert all of the unsigned number to 0 and 1, so that computer will understand it. Okay, so there are two ways for the unsigned binary, which is first the conventional binary representation, which we already discussed in our lecture 1 last time. And then but the second method is BCD. BCD is binary coded decimal representations. Okay, so this conventional binary representation is like what we have done in our first lecture, which is you multiply each of the number with its position. So we will also see in the details in our next slide. Okay, so this is the conventional binary representations. So this is simply this method simply recognize that there is a direct binary equivalent for any decimal integer. Okay, so it will store any whole number as its binary representation. So if you forget on how to convert the decimal number to the binary representations, please refer back to our chapter 1. Okay, so the range of integers that can be stored is determined by the number of bits available. Okay, so in this method, we will use multiple storage locations to expand the range of the integers to be handled. Okay, so after the number or the decimal number converted to the binary representations, it will be stored in the processor, which is, if you guys remember, in our processor there will be a different part kan. So one of the part in the processor we called as there's a ALU kan, if you remember lah, last time we have learned in your previous semester. Okay, so in the processor there's a ALU, there's a registry. Okay, so all of the binary number, all of the decimal number that is converted to the binary, is stored in the processor registry. Okay. Okay, so this is the example on how you convert the decimal to so how you store the binary representative after you convert the decimal to registry. Okay, so for example, this one. Let's say you have 32-bit data word. 32-bit data word ini means that there are 32 0 and 1, 0 and 1. It will be, there are 32 digits lah, 0 and 1, 0 and 1. Okay, after you change some number from decimal to binary, and then you get 32 bit, and then that 32 will be stored in the registry, and then this is how they will this is how the registry will store the system. There will be a part 1, this meaning if you remember last time in our lecture 1, there are when there are number of binary at the most significant MSV. This is the most significant value at the left. At the left is the number of binary which has most significant bit, MSB. And then at the most right binary number, it will be the less significant bit, meaning for the first add significant bit, it will be stored at the top, and then it will be, and then the next add bit will be stored here at the second row, and then the next add bit will be stored here at the third row, and then followed by the next bit. Okay, so understand this one? It will store when you have a 32 bit, it will be divided by 8 bit each. And then it will be stored in the memory like this. Start with the most significant bit first at the top.
Miss,
Okay, so,
can zoom in?
yes. Yes?
Zoom in.
Oh, zoom in. Okay. Yeah, this one. Let's say you have oh yeah. So do you understand this part?
Oh yeah.
Okay. Okay, so we proceed to how you convert the binary to the coded decimal. Okay. So we finish with the conventional binary representation. This conventional binary representation is the usual way of how we convert the decimal to the binary, like we have learned in our chapter 1. And then we proceed to the second method of representing unsigned number, which is binary coded decimal. So we call it as the short form is BCD. Okay, so the number is stored as a digit by digit binary representation of the original decimal integer. For example, each decimal digit, okay, so in this BCD, each decimal digit is individually converted to binary 4. I mean in binary, and then each binary will have 4 bits per digit. Okay, for example, if previously when we are converting this decimal to binary using the conventional way, we will do like this one, kan? We will, if you remember, we will do division, kan? Division by 2, division by 2. Okay, so but using the BCD, we will make this individual decimal number. You will, we will need to convert it to its 4-bit digit. Okay, for example, 8 is equal to 1000. If you guys remember, this position is 2 1. Sorry, I will write. This position is sorry. So, if you remember, this position is 2 power of 0. This is position 2 power of 1. This is position of 2 power of 3. And then this is position 2 power of, yes, this is 2 power of 3. Okay, so 2 power of 3 equal to 8. Kan? So that's why it will be 1000. Okay, so for 6, 2 power of 0 will be 1. Wait, I will write sini. Okay. Okay, so 2 power 0 equal to 1. 2 power by 1 equal to 2. 2 power of 2 equal to 4. 2 power of 3 equal to 8. Okay, so we will multiply 1 with 8. So we will have 8. So that's why the binary representations for 10 is for 8 is 1000. Okay, so similar here for 6. Okay, so 6, 1 multiply 4 is 4, and then 1 multiply 2 is 2. So we didn't calculate 0 because it, of course, it will resulting in 0, right? So 4 plus 2 will equal to 6. So that's why 6 is 0110. Okay, so this is the binary coded decimal, meaning we convert each of these decimal to its binary representative, but in 4-bit digit. Okay, so we will get 1000 equal to 8, 0110 equal to 6. Okay?
Okay.
Okay. So this part, I think it is simple. Okay, so this is the comparison between the conventional binary representation with the BCD. Okay, so actually BCD is a little bit difficult because dia punya calculation is more difficult, and then any product or sum of any BCD integer that more than 9 must be reconverted to BCD each time to perform the carries from digit to digit. Okay, so we will know about that in our next slide lah. What does it mean by this one? Okay, so this is the comparison of calculation between the conventional binary and then the BCD. So this is the conventional binary. Sorry, this part is conventional binary. So let's say we want to convert 72 in decimal using the conventional way. Is we will get this one 10 00 00 1 and then 00 and 0, and then we know that each of these weightage is this one. Okay, that's why I said just now. So you guys just remember this is the value of each of these weightage. Okay, so the first value must be 1, and then the second value must be 2. So this is static value that we need to remember later. So no need to do this one because of course and for sure dia punya answer is sama macam ni. Okay, so this is the conventional way. We change it by 72, we divide by 2, and then lastly we will get this. So this is the conventional way. But for when we are using binary code decimal, we will get something like this, because we will separate each of this decimal digit and then get its representative binary number for each of this number. Okay, so for example 2, the first 4 bit here will be 0 1 0 0, because the position of we will get 2 at the position of 2 power of 1. So you will put 1 here because this is the value of this decimal. Okay, so for the 7, we will get, this 4 bit will representing the 7. So we will have 1 1 1 0, because 1 plus 2 plus 4 is 7. So you will get your binary representative for 7 will be 0, 1, 1, 1. Okay, so this is how different binary BCD and conventional way of converting the number or unsigned number. Okay, so for this one, because I think the calculation here is a little bit complicated, so I prepare another example, which is this. So this is actually more in details about BCD. Okay, so this is how you convert the binary that the binary that the binary number to BCD. Okay, so this is not the decimal to BCD. This is the binary number, given the binary number, and then you need to convert it to the decimal. So how is it is? So this is the how. Okay, so I will directly go to the step of how to converting the binary to decimal and then lastly to BCD. Okay, so in order to convert the binary number to the BCD, you need to convert the binary number to decimal first. After that, barulah we can convert the decimal to the BCD. So this is the step. Okay, so the step 1, you need to convert the binary number to decimal. So this is we have already learned in our lecture first. So you need to convert all of the binary number to the decimal first. After that, we need to convert the decimal to the BCD. Okay, so for example, we want to convert the best 2 number or binary number. This one, this is best 2. This is should be 0. This should be 2 small here, but I think because the editor cannot get that this number 2 smaller, so they put it like this lah. Okay, so this is the number in base 2. Okay, so we want to convert this number in base 2 to BCD. So the first way is we need to convert this base 2 number to decimal first. So this is like what we have learned previously. So we need to multiply each of this position to the weightage value. Okay, so we will get 29 in base 10, which is in the decimal. So we will get 1,1,1,1,0,1 equal to 29 in decimal. After that, we will convert the decimal just now, the 29, to BCD number. Okay, so we will need to convert each digit into the group of 4 binary digit equivalent. Okay, so 29 is equal to 0, 1, 1, 1 for 9, because 9 is equal to 0, 1, 1, 1, and then 2 is equal to 0, 0, 1, 2. 0, 0, 1, 0. Okay, so the answer is this one. So this is the BCD for this one. Okay, understand yang ni?
Okay.
Okay. Sorry, Noel, I cannot hear you.
Yeah.
Okay.
Okay.
Fedor? Okay, Kelvin?
Yeah.
Okay, so we proceed. So this one I directly because I think it is a little bit hard to understand, so I cancel this one. So I will update this later in our Google Classroom. Okay, so just now we already learned about two method of converting the unsigned integer, but now we will proceed to the sign integer representation. Okay, so like I said previously, there are three methods of converting or representing the sign integer into the computer understandable integer, which is the 10001 Okay, so this is a little bit it is easy actually, simple, but a little bit tedious. There are small steps that we need to follow. Okay, so the first method is sign magnitude. And then the second is 1 complement. And then the third method is second complement. Okay, so like I said previously, these two method has problem because it will produce when you convert all of the number, all the negative and positive number into binary, it will produce ambiguous result because there will be two value of 0. Okay, but that weakness is improved or solved by this third method, which is the 2 complement. So we will dig into deep about all of these methods in our next slide. Okay, so we proceed to the first method, which is the sign and magnitude representations. So this is actually I think it is easy because when you have this binary number and then you want to indicate either it is positive or negative, because because we cannot represent negative in, I mean, computer doesn't understand negative kan, because it only understand 1 and 0. So how we will make computer understand that it is actually your number is actually a negative number. So the first method is by using the most significant bit, meaning this one, the leftmost bit, which is the most significant bit, as the indicator to say that either the number is negative or positive. So the expert that created this method says that 1 will indicate the negative sign, and then 0 will indicate the positive sign. Okay, so don't confuse that, because usually 1 usually positive kan, and then 0 usually negative. But in sign and magnitude representation, it is different lah. It is opposite, meaning 1, if the number or if the most significant bit number of that binary number is 0, meaning this number is positive. But if the most significant bit here is 1, meaning this number is negative. Okay, so this is the example of number lah, like I said just now. All the positive number is like is like your the price lah, the price of each of the item in the shop kan. So there will be no negative value lah for a price. But for the sign number, for example, the temperature, it will need to indicate either positive or negative value, because there's a number of negative and positive in temperature. Okay, so the range of number to be represented are now smaller, 4-bit binary, meaning 1 bit for sign and then 3 bit for the magnitude. Okay, so this one, what does it mean is only this, I mean the range of the number is become smaller, because if previously it is 4, Now only 3, because the MSB or most significant bit is already representing the positive or negative value. Okay, so the range of number to be represented are now smaller. If previously it is 4-bit binary, and then 1 bit for used for the sign, and then 3 bits for the magnitude. So the 3 bits is the magnitude. This is for the sign. So it can be used to represent this formula, meaning 2n minus 1 minus 1 until 2 power of n minus 1 n minus 1. This is the range of the number that can be reached. So this is, for example, 2 power of n, and here is from this one. If this is 4, so n is 4. So 2 power of n minus 1. N is 4. So minus 1 will be 3. So 2 power of 3. 2 power of 3 is equal to 8. So 8 minus 1 equal to 7. Okay, so you will get this range. When your number is only 4-bit, so the range of the number that can be represented is from -7 until +7. Only until that number. So if, for example, kan later we will see later if the addition or subtraction of this binary number, it is over this number, out of this number, so it will cause some problem which we called as overflow and carry. So we proceed first now. Okay, so this is the sign and magnitude representations where the first MSB or most significant bit will represent the sign, either it is positive or negative. So when you see here, this is the 0, so it means it is positive. So this is positive. And then what 64, because only this one yang have value kan. So 64 plus 8, because only 8 has value here. And then so this number representing positive 72. So this is the second example. Because the first MSB is 0, so this is positive number. And then we get the value of each of these bit. So we will get 64 plus 8, because 64 plus 8 plus 4 plus 2. So you will get positive 78. But this is the example of the negative bits on how we will, sorry. So this example is the negative number. So the first MSB is 1, so this is negative. So you will get 64, negative 64 plus 8, because only 64 and 8 has the number here. So it will produce negative 72. Okay, so similar with this one lah. We see this because this is the first sign. The first number is indicating the sign. So we will not take this into calculation because this is a sign. This is only indicating the sign. Okay, so we will get the value for the rest of the number except for this one. Okay, so we will get negative 78. Okay, so these are the disadvantage of the first method for the signed integer number, which is it can result in the possibility of two different bit patterns having the same binary value. Okay, for example, positive 0 and negative 0 would be this one, because this is the positive and then this is the negative. Kan? So you guys can see the problem, kan? Because there will be two value for there will be two different bit pattern for 0. So that's why we have positive and negative 0. So that is the problem. So we can see that using this method, there are two representation for 0, a positive 0 and then also the negative 0, because this one representing the negative. So which can cause big complication for computer and digital system. So we cannot use this method. So the expert come out with the next method, which is the ones complement. In this ones complements method, the expert use the inversions, meaning to say that each complement of 1 will be, each of the binary will be it will be inverse to its complement punya number. For example, if it is 0, it is 1, so it complement will be 0, kan? So we will change the 1 into 0 and then 0 to its 1. So numbers beginning with 0 are positive, and also the numbers beginning with 1 are negative. So this is the same rule with the first method, but only it add new rule, which is it will change the 1 into 0 and then 0 into 1. Okay, so another method which we can use to represent negative binary number in a signed binary number system, sorry. So it says that this one complement is another alternative method rather than the first one just now, the sign and magnitude. Okay, so positive number are also known as the non-complements remain unchanged as before with the sign magnitude number. So we will, in this method, we will not change anything to the positive number, but we only change the negative number. Okay, so the negative number are represented by taking the one complement, meaning the inversion of that number, of the unsigned positive number. And then since positive number always start with 0, then complement will always start with 1 to indicate the negative number. Okay, so, but this method also produce two representative of 0, meaning the problem from the previous method still remain, which is we have two type of 0. Okay, so this is the example of the first complement. We will make that for the positive, for the negative number of this value, which is the 1 or 0, we will not change anything on this, but to get its negative value, we will need to inverse each of these. Okay, so we will need to inverse each of these to become like this. This one become 0, this one become 0, this 0 become 1, and then 1 become 0, 0 become 1, 0, 1 become 0, 1 become 0, and then this is representing the sign, which is negative. So actually, the calculation for this, it is this one is a little bit wrong, but this should be the calculation here. This should be negative 107. But for this one, I will get back to you guys later. I mean, in our next lecture, because I haven't changed this calculation here. So this one, I will explain to you guys later on how we will represent the negative value using this method. Okay, so because this one is wrong. Okay, so we proceed that because I will explain this later after I get the right figure. Okay, so we proceed to the second complement. So this second complement, it will find the first complement first, and we will add 1 to the complement's value, and then we will get the two complement representation. So if you guys don't understand, don't worry, because I have found a very good video that will make you understand how this two complement solving the problem of the previous two. Okay, so we will watch this video first lah.
Already be familiar with binary. For example, the sum 101 is 1.25 in decimal.
Can you guys hear the voice, the sound?
Can, but very low.
Very
volume.
soft lah, kan?
Yeah, very soft.
I will share the link lah in our chat. Okay, you guys watch this first.
You might already be familiar with binary. For example, this is 101 is equivalent to 5 in decimal, and that's because this is the ones place, this is the twos place, fours place, eights place, 16s, 32s, 64s, and 128s. And we have a 1 in the fours place and a 1 in the ones place. 4 plus 1 is 5.
Guys,
So this is fine.
I think don't watch it first lah. Later lah, because I think if I proceed later, you guys can watch it after our lecture. Okay? Okay, better. Okay, so if you read this one, memang lah, of course you will not understand lah. I mean, because it is words kan, in words. So we will see in our next slide. Okay, so the video that I give you just now is really it is really explain why the three methods, what is the weakness, and then how it is solved with the third method here. Okay, so we proceed dulu lah. Okay, so this second complement, how we will do it is, it says here, you need to find the first complement first, or sorry, the one complement first, and adding 1 to the inverse bit, meaning you need to change first the number. For example, this one, you change all of this from the inverse bit first. After that, we add 1 to that inverse bit. So what does it mean is like this. After you change, let's say you have this the number in decimal 4, and then this decimal number, when we change it to binary number, we will get this, because why it is there's 8 bit here, because in 1 byte, in 1 byte, it is equal to 8 bit kan. So when the computer store number 4, it will store it like this. Although the only value here is this one, because this is representing 4. And if it is in 4-bit, you can just write it in like this lah. But because computer are using 8-bit, which is 1 byte, so we need to write it in one byte, which is 8-bit. Okay, so we do the ones complement first, meaning we inverse all of this number. So we will get its inverse number. Okay, so after that we plus 1, we add 1 to that number. Okay, so using this formula, you will get this one. And then, miraculously, orang bilang, secara ajaibnya, when you add all of this, it will produce -4. So this is what it should, how it should be lah. When you have positive number and then you apply the second complement, sorry, bukan second. You apply the 2 complement method to this number, you will get its negative binary. So in computer letter, the decimal 4 will be stored as this one, and after that, its negative will be stored as this binary number. Okay, so in that video letter, when you watch, you will know how they get that formula to come out with this step. Okay, but this is how we can, this is, forget about the first 2 method, because it will produce wrong negative number. It will produce a wrong negative number lah. But using this method, you will get the right and correct value of negative if you are given the positive number. But don't forget the one complement punya method lah, because in the 2 complement it use complement method. It used 1 complement method, which is to inverse each of the number here. Okay. Yang this one can understand ka?
Okay.
Can.
Okay.
Yeah.
So later, when you have the tutorial questions for this is the step lah. This is the step of how you can do or calculate the negative number using the 2 complement method. Okay, so we proceed to how we can subtract or how we can do subtraction using the 2 complement method. So this is the example. Let's say, actually this is a little bit confusing lah when they write it like this. So I rewrite these questions to this. So actually the question is only 30 minus 10, but because we want the negative number, so that's why I rewrite it again like this, because when this one macam it is like 30 minus 10 multiply 30 macam apa kan? So it is confusing. So I rewrite these questions to be like this, because the question is actually only 30 minus 10. Okay, so I rewrite it like this, and then in decimal, of course, it is easy lah. We know that 30 minus 10, it will be 20. But how we will do it using the using the second complement. Sorry, I keep saying second. 2 complement. It is actually 2 complement. to complement is using this way. Okay, so first we need to convert the second number first, the number that you want to subtract from the original number. Okay, so first you need to reverse the second number first, which is 10. So 10 in decimal will be representing like with this number. And then after that, you reverse, meaning you apply the the 2 complement here, and then you get the value, kan? Because it is we want it in the negative. So that's why we need to inverse 10 first, because we want to get the negative value, negative representative of 10. So that's why we need to impose the 2 complement method to 10, because we want to get this one. So after that, barulah we will add. So it is actually minus, but the way we will do it is we will add the inverse number of 10 to the 30. Okay, so after that we will get the punya value. But in this way, after we add, so we will get this one. But this number, the MSB, it will be ignored, because we will only need 8 bit of number. So after you add, you will get this one, which is you can get 20. So this one can understand?
Can.
Okay. So this is actually the last topic that we will cover today, which is the overflow versus carry. So actually, this one we call it as overflow, and then what we carry over on top of this calculation, we call it as a carry. Okay, so what macam 1 plus 1 equal to 1 0 kan, and then we put 0 here, and then we carry 1 at the top there. So it is a carry number. So this is the discussion about the overflow and the carry, because in the previous example there are overflow here kan. Okay, so in this method we will ignore the overflow. Okay, so here is the comparison between the overflow and the carry. Okay, so the overflow will be usually happen in sign arithmetic operation. In the sign arithmetic operation, just what happened in this lab, because this is one of the sign arithmetic operations, kan? So overflow usually happen to the sign arithmetic operation. So overflow occur with respect to the size of the data type that must accommodate the result. Okay, so when, for example, if the number that you add, is 8 bit, and then when you have excess punya bit, so it is the meaning of this overflow occur with respect to the size of the data type that must accommodate the result. Okay, so that is when your bit should be 8 and you are exceeding that 8 number, so it is when the overflow occur. Okay, so overflow indicate that the result was too large or too small to fit in the original data type. Okay, so that overflow just now indicate that the result was too small or too large to fit in the original data type. And then overflow can be detected when both the most significant bit of the operands are the same, but they are direct opposite to the most significant bit of the result. Okay, so this is what it says here. Both of this number has the same bit, which is 8. But it happened when the most significant bit, last bit here, the most significant bit, difference from the result of the most significant bit. So what does it mean is the most significant bit of the result here is exceeding the bit of the operands. This is the operands. Okay. So the carry problem is it is usually happen in the unsigned arithmetic operation. So the unsigned arithmetic operation usually will have this problem, which is the carry. So carry occur when the result of the unsigned arithmetic requires a carry out of the most significant bit. Okay, so when you adding or when you do arithmetic operation on the unsigned arithmetic just now, and then it will also produce something like this. When you add, I think it will produce something like this, like it is out of the bit, meaning it is the result of the bit of the result is exceeding the operandnya number of bit. Okay, so carry indicate that the result is too large to fit in the original data size. Okay, so carry can be detected when there is an extra bit generated to the left of the most significant bit of the result. Actually, it is macam like kind of similar lah, but the overflow, they call it overflow if it is happen in the signed arithmetic operation, and then they will call it as a carry when it is happen in the unsigned arithmetic operation. Okay, so the similarity between these two are the carry and overflow are two conditions which can occur during addition and subtraction. Okay, so the condition affect bits in the flag register, which can then be tested by conditional jump instruction. Okay, so for this topic, we will only stop until this, because I will find a good example first for this explanation, and then I will give you later in our Friday lesson. Okay?
Need a lot of practice.
Yeah, itulah. That's why you have to do your tutorial first, because we need one by one. We need to do it by one by one. When you do when we finish our tutorial one, and then you directly do your tutorial one, because when we have done with our first lecture, you guys need to do your tutorial one directly, because nanti you forgot, because there's a lot of step kan to remember. Yeah, so after this I will upload the tutorial, but you will need to only answer until some questions jalan. Don't answer all, because we only until this one kan, second complement and this one in page 23. So for the rest of the time ini, I want you guys to watch first lah. Watch first what I have give you just now. It takes about 13 minutes too. And then after that, you can ask me if you have questions lah about that video. Okay? Okay.
You might already be familiar with binary. For example, this is 101 is equivalent to 5 in decimal, and that's because this is the ones place, this is the twos place, fours place, eights place, 16s, 32s, 64s, and 128s. And we have a 1 in the fours place and a 1 in the ones place. 4 plus 1 is 5. So this is fine, but how might we represent a negative number? So let's say we wanted to represent negative 5. Well, there's a couple ways we can do that. One way is to take this 128th place, and instead of using that as the 128th place, use that as a sign. So change this to a 1 here to indicate that this is negative, and then the rest of it is the same. 1, 0, 1. And so this would be 5 here, and then instead of this representing 128, it represents that the number is negative, so negative 5. Now, of course, it's important to know how many bits you're working with, right? Because if we're only using 4 bits, then a 5 would be 0, 1, 0, 1. That's equal to 5. But then we're going to use this top bit here. In this case, we're only using 4 bits, so the top bit is this 4th bit, and so a negative 5 might be a 1, 1, 0, 1. And now instead of this being the 8th place, this is actually representing the sign. So this would be negative 5, and this would be 5. So it's important to know how many bits you're working with so that you know which bit is the first bit, and therefore which bit indicates what the sign of the number is. So to keep going with this example, we can look at just regular counting in binary here. Of course, if we have all zeros, 0, 0, 0, 0, that's equal to 0. And then if we have a 1 in the ones place, that's equal to 1. We have a 1 in the twos place, that's equal to 2. A 2 and a 1, that's equal to 3. And then, of course, a 4 is 4. A 4 and a 1 is 5. A 4 and a 2 is 6. A 4, a 2 plus a 1 is 7. So that's simple enough. And then if this first bit here is indicating our negative sign, then we can go backwards too. So if we have a negative 1, that's negative 1. A negative 2, a negative 2 and a 1 is 3, and then a negative 3. Negative 4. A 4 and a 1 is 5, with a negative is negative 5. 4 and a 2 is 6, so this is negative 6. And then a 4 plus 2 plus 1 is 7, and that's a negative 7. And so this is our sign bit. And so this first bit is our sign bit, and then these other bits are just our 1, 2, and 4 place. Simple enough. A couple weird things about this, though. One is that you'll notice there's a negative 0, right? Because you can have 0, 0, 0, and then it can either be a 0 in the sign bit place or a 1 in the sign bit place. So you can have, there's a difference between 0 and negative 0. So that's kind of weird. The other thing that is maybe a little bit inconvenient, and we'll look at some other approaches that don't have this problem, is if you try to add these things together, things get kind of weird. So let's say we want to add a 5 and a negative 5. So normally 5 plus negative 5, you would expect to get 0. Simple enough. But here if we look at 5, 0, 1, 0, 1, and negative 5 is 1, 1, 0, 1. If we add these together, 1 plus 1 is 2, which would be a 0 and then carry the 1. 1 plus 0 is 1. 1 plus 1 again is 2, but we'll put that as a 0 and carry the 1. And then here 1 plus 1 again is 2, so a 0 and carry the 1. So in this case, what we're seeing is 5 plus a negative 5 is not 0, it's 0, 0, 1, 0, which, well, and we have a carry. So we have a carry coming out of this 1 bit that we don't, if we're working with 4 bits, we're going to ignore this carried bit. And so we have 0, 0, 1, 0, which is 2. Well, so that's kind of weird. If we're adding 5 and negative 5, we wouldn't expect to get 2. And you can try adding some other things here, and it doesn't work. So let's take a look at another scenario here. This is called ones complement. What this is again, everything from 0 to 7 is the same. Same as we saw before. And this first bit here is all zeros, so we know that these are all positive. But what we do for the negative numbers is we actually just flip all of the bits. We take the complement of all of the bits. So, 2 here is 0, 1, 0. Well, 0, 0, 1, 0. Negative 2 is 1, 1, 0, 1. So we're just flipping each of those bits. So we flip the 0 for a 1, we flip the 1 for a 0, we flip the 0 for a 1, and so on. If you look at each of these numbers, so 5 is 0, 1, 0, 1, negative 5 is 1, 0, 1, 0. So what happens with this? So we still have this kind of strange thing where we have negative 0, and we'll come back to that in a minute. But what we can do is we can try to add some numbers. So if we add 5, so 0, 1, 0, 1, so that's 5, and negative 5, 1, 0, 1, 0, if we add those, adding negative 5 here, what we end up getting is 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 0 is 1, 0 plus 1 is 1. We get 1, 1, 1, 1, which is negative 0. So that's closer, right? 5 minus 5, you'd expect to get 0. Negative 0 is, I guess, the same thing. So that's pretty good. And that actually works for any of these. We can do 3 minus 3, or 3. So 3 is 0, 0, 1, 1. Negative 3 is 1, 1, 0, 0. So this is 3 plus negative 3. If we add these together, so 1 plus 0 is 1, 1 plus 0 is 1, 0 plus 1 is 1, 0 plus 1 is 1, we get 1, 1, 1, 1 again. And so again, 3 minus 3 is negative 0. So this is definitely doing a lot better than here, where we were saying 5 minus 5 was 2. That's definitely not right. So negative 0, definitely a lot closer. Let's try some other things, kind of see if we can see a pattern here. So if we did, let's say 5 plus negative 3, so 5 minus 3, let's see what we get there. So 5 is 0, 1, 0, 1. And negative 3 is 1, 1, 0, 0. So 1 plus 0 is 1, 0 plus 0 is 0. 1 plus 1 is 2, so we'll put a 0 and carry a 1. And then 1 plus 1 again is 2, so we'll put a 0 and carry a 1. And so if we ignore this first bit here, because we're working with 4 bits, we get 1. So 5 minus 3 is 1. That's close. It should be 2, but let's see what happens if we do, let's say 6 minus 2, or 6 plus negative 2. So 6 is 0, 1, 1, 0. Negative 2 is 1, 1, 0, 1. 1, 1, 0, 1. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 2. Put a 0 and carry the 1. 1 plus 1 is 2. So put a 0 and carry the 1. Again, ignore that first bit because we're working with 4 bits. So 0, 0, 1, 1 is 3. So we're saying 6 minus 2 is 3. Close, but we're definitely seeing an interesting pattern here. In fact, if we look, these places where we're getting this negative 0, if we just go down 1, we see 0, which is what we want. Here, 5 minus 3, we'd expect to see 2, but we're seeing 1. So if we just go down 1, we'd actually see a 2. 6 minus 2, we'd expect to see 4, but we're actually getting 3. But if we go down 1, we get the right answer. So we could just always add 1 to each of these. Of course, it's kind of weird to say add 1 to negative 0 to get to 0, but if you kind of bear with me a minute, you'll see that if we add 1 to the binary value and it flips over, you do get to the right thing. And here you get to the right thing. So the ones complement, just flipping all of these bits is close. It's very close. It's off by 1 on all of our arithmetic. And it also still has that nice property that we saw with the sign bit, which is, you can look at this first bit and you can tell these are all negative numbers. And if the first bit is 0, then they're positive numbers. So it seems like the ones complement has a lot of the, a lot of nice properties, that you'd have in the sign bit. The one thing that's, well, I guess it's not too bad, is that to invert or to negate a number, if you're going from 5 to negative 5, with a sign bit, all you'd have to do is flip 1 bit. You just flip that first bit to a 1 and you get to negative 5. With the ones complement, you have to invert each bit. So it's a little bit more work, but of course inverting bits is pretty easy to do in hardware. If we're building hardware to do this, if we're building a computer, it's going to be doing some math. So ones complement seems pretty good, but it is off by 1. So what we can do is look at another scenario, which is 2's complement. And if we compare 1's complement to 2's complement, it's basically the same, except what it does is it gets rid of this negative 0. So instead of having negative 0, we just go right to negative 1. Negative 2, 3, 4, 5, 6, 7. And the kind of weird thing here is we have a negative 8, and we don't have an 8. But the nice property about this is that all of our math works out very nicely. So if we have 5 minus 5, 5 here is 0, 1, 0, 1. And so that's 5. And negative 5 is 1, 0, 1, 1. So 1, 0, 1, 1. And if we add these things, if we add negative 5, 1 plus 1 is 2, so we'll put a 0 and carry the 1. 1 plus 1 is 2, so put a 0 and carry the 1. 1 plus 1 is 2, so we'll put a 0 and carry the 1. And 1 plus 1 is 2, so put a 0 and we have a 1 that we're carrying. And so you'll notice that each, when we're looking at the negated version of something, when we add each of these place values, we get a 2 each time, and that's why it's called 2's complement. But in any event, you see that we end up with 0, which is just what we would want when we add a number to its inverse. And in fact, you can try it with any of these numbers, and you'll find out that you get all zeros. So let's try 6 minus 2. So 6 is 0, 1, 1, 0. That's 6. And minus 2 is 1, 1, 1, 0. 1, 1, 1, 0. And if we add these together, so if we add our negative 2, whoops, negative 2, adding negative 2 there. 0 plus 0 is 0. 1 plus 1 is 2. So we'll put a 0 and carry the 1. 1 plus 1 plus 1 is 3. So that's a 1 and a carry a 1. And the 1 plus 1 is 2. So 0 and carry a 1. And again, we ignore that 5th bit there. And so 0, 1, 0, 0 is 4. And sure enough, 6 minus 2 should be equal to 4. So this 2's complement works pretty well. And it also has this nice property, again, that first bit is a sign bit, right? Because all of these negative numbers have a 1 there. And what's even more interesting about 2's complement is if you look at the place values, it actually makes sense. This is our 1's place, this is our 2's place, this is our 4's place, and this place here, it looks like a sign bit, but really it's a negative 8's place. And you can see when we have a negative 8 and all zeros, we have a negative 8. But if you have a negative 8 and a 1, you get negative 7, right? If you have negative 8 and a 4, you get negative 4. If you get negative 8 plus 4 plus 2 plus 1, you end up at negative 1. So this bit value actually has a mathematical meaning, which is why our math works out. So it's pretty cool. The one thing that's a little bit harder with 2's complement is negating a number. So if we want to go from a 5 to a negative 5, it's kind of a two-step process, right? So 5 is 0, 1, 0, 1. The first thing you have to do is take the 1's complement, 1, 0, 1, 0, so flip all the bits. So you're just inverting everything. That's easy enough. But then you have to add 1. So you invert, and then add 1. So to add 1 to 0, 1, 0, 1 is just 1, 0, 1, 1. And then this invert, so this is 5, then we invert it, and then we add 1, and that gets us to negative 5. And you can see negative 5, 1, 0, 1, 1, 1, 0, 1, 1. So it's a little bit more work to go from a positive number to its inverse, because you have to invert it and then add 1. But what you'll see in the next video when we build a circuit that can add and subtract, you'll see that it's actually not too hard to build this in hardware.
Okay, guys, have you finished watch that video?
Yeah. Need to write. Do we need a table for the numbers?
Okay, sorry, I cannot hear you.
Do we need to be like write the table on the left?
No, no, no. That's what I want to tell you guys now. Okay, so what I show you just now is the video that explaining how is the evolutions of the methods that is what prepared by the expert, how they come out with the first method with this, which is the sign and magnitude, the name sign bit lah. And then after that they overcome the problem of the sign, they come out with the first the one complement. After that they come with the second the two complement. So don't worry, you don't have to do all of that table and then the all of the paper. So what you need to remember is the formula saja. So how the formula of the two complement, which is in your slide 21. Sorry, I am presenting my screen first. Okay, so can you guys see my screen now?
Can.
Okay, so what you need to remember is, or what you need to know after you watch that video is the end conclusion just now in that video, which is to come out with the negative number when you are given a positive number. The first step you need to do is you inverse the binary number of that decimal positive number first. You inverse. Okay, first step is inverse, and then after that add 1 to that inverse number. After that you will get the addition punya result. After that you will do this. So this is the only step you need to do. So you need to remember. So just macam bookmark or just highlight this step or this page. Okay?
Okay.
Kelvin, okay?
What highlight?
Yes.
What do you mean highlight?
You I cannot really hear you actually. You want to highlight? You said you highlight.
No. What do you mean? What you said just now?
This one. I mean you what you not highlight lah. You bookmark, kira macam bookmark lah this page. This is the end. This is the way that you need to solve, that you need to do when you are solving or when you are looking for negative version of a number. Meaning the conclusion or the summary of the video that we watched just now. Okay?
Okay.
Okay, so kira macam you bookmark this page lah. Bookmark. I don't know how to bookmark this in PDF, but just put somewhere in your notes, apakah? Meanings that the page 21 is important. Okay, so we will stop. We stop in this page. So next we will continue at the page 24. Next, our next class. Okay?
Okay.
Okay, so do you have any questions?
So far,
No. Okay, so Noel? Sorry, Noel. Ferre, do you have any questions? Okay, so I will upload the tutorial 2, and then we will discuss the tutorial 2 on next week Friday. Next week Friday kah? Next week Wednesday. Next week Wednesday. So tutorial 1 will be this week Friday, and then tutorial 2 will be next week Wednesday. Okay, so if you guys don't have any questions, we can end our sessions now lah. I will upload the tutorial later and I will inform you guys in the WhatsApp group.
Okay.
Okay. Bye.
Okay. Thank you, Miss.
Okay.